Hi guys, I hope you're all doing great and safe over there. This is Chandana and today I'm back with another video. In today's session, we will be discussing about the subject digital communication, under which we will be discussing about the topic Gram-Schmidt orthogonalization procedure. Let us see what is meant by Gram-Schmidt orthogonalization process. The Gram-Schmidt orthonormalization process is a procedure for orthonormalizing a set of vectors in an inner product space. Most often, the space R per n provided with the standard inner product in mathematics, notably linear algebra and numerical analysis. Let us see, why do we use Gram-Schmidt orthogonalization. The Gram-Schmidt process is used to transfer a set of linearly independent vectors into a set of orthonormal vectors forming an orthonormal basis. It allows us to check whether vectors in a set are linearly independent or not. The procedure contains two steps. Here, let us consider M is an energy signal which varies from S1 of t, S2 of t to Sm of t. Thus, Gram-Schmidt orthogonalization allows us to determine a set of n orthonormal signals such that each Si of t can be expressed as linear combination of n orthonormal files. Let phi 1 of t, phi 2 of t, so on till phi n of t are orthonormal that has to be determined. Here we know the formula that Si of t is equal to summation j is equal to 1 to n Sij phi j of t, which varies from 0 lesser than or equal to small t lesser than or equal to capital T, and I is varies from 1 to 2 till m. We consider S1 of t, S2 of t till Sm of t signals to find out phi 1 of t. Here we know that integration of 0 to t phi 1 of t phi j of t is dt is equal to 1 when I is equal to j, and it is 0 when I is not equal to j. Finally, the computing step starts. The step 1 is from equation 1, set all coefficients Sij is equal to 0 except S11, that is S12, S13, S14 till S1n is equal to 0 except S11. Here we have the formula phi of 1 is equal to S1 of t by S11. So on squaring both the side of the integration, we get this particular solved solution, that is phi 1 of t is equal to Si of t by root E1. Now here we are entering to step 2. In equation 2, all the coefficients except S11 and S21 and S22 to 0. So whereas in the previous equation, step 1 we consider S1 of t, now we are considering here S2 of t. The formula is 2151 of t plus S2252 of t is equal to equation A. Multiplying both sides by phi 1 and integrating over t, doing this process, we get S2 is equal to integration of 0 to t, S2 of t and phi of t. So if S21 is known, then equation A can be written as G2 of t S double 2 to phi of t is equal to S2 of t S21 phi of t. Squaring and integrating over the period 0 to t, we get the final equation. Here, squaring and integrating all the given particular equation, we get square root of E2 minus E SS1 to 1 square. From equation we get to know that phi 2 of t is equal to 1 by s22 s2 of t minus s21 s1 of t by s1. Therefore, phi 1 is equal to s1 of t by s2. In this fashion, we can determine the other orthogonal functions and coefficients using the same process. The rest of the orthonormal and orthogonal functions can be determined. So we can generalize the formula or the equation as g1 of t is equal to si of t minus summation g is equal to 1 to I minus 1 sij phi j of t. So here sij formula is given as si of t phi j of t dt, where j is varied from 1 to I minus 1. When we consider I is equal to 1, then we'll get phi of 1 is equal to gi of t by root of integral 0 to t gi square of t dt, where j varies from 1 to n. Now, let us consider a numerical and see how this solution can be performed. Consider the signal S1 of t, S2 of t, S3 of t, and S4 of t shown in the figure. All the all the four signals is given in this figure. We wish to use Gram-Schmidt orthogonalization procedure to find orthonormal pieces for this set of signals. Once we know the procedure to solve, it is very easy to find out the output. In step 1, we note that the energy of signal S1 is 0 to t S1 square of t dt. That is, for S1 of t, we will be considering this particular waveform. So here, this is the formula, and for this particular waveform, the period varies from 0 to t minus 3. So here integral 0 to t minus 3, and the given output is 1 year. The unit is 1, so 1 square is equal to dt. We all know integration of 1 is equal to, with respect to t we get t, so it is t by 3, and the first basis function of phi 1 of t is therefore given as, we know the formula, phi 1 of t is equal to s1 of t by root e power 1. So here we can define the period. It is s1 of t by root e1, so we can write s1 of t is root 3 by t, where it varies from 0 t less than or equal to t by 3, and 0 it is otherwise. Let us go for the second signal. Evaluating projection of S2 of t onto phi 1 of t, we find that we know the formula S2 of t phi 1 of t dt. So here the period is from 0 to t by 3, 1 into root 3 by t dt. So as it is, we will get to know that it is root 3 by t. The energy of the signal S2 is given as, we know the formula, interval 0 to t S2 of t. So here the period varies from 0 to 2t by t, and one integration of 1 is t, so we get 2t by 3. This will be the solution for this signal S2 of t. And now the period of the particular S2 of t is given here. Let's go for the waveform S3 of t. Here S3 of t is equal to 0 to 2 S3 of t phi of t is given as 0, and coefficient S32 equals to 0 to 2 S3 of t phi 1 of t dt. So the period varies from t by 3 to 2t by 3. So the solution for S32 is root 3 by t. The corresponding value of intermediate function gi of t within I is equal to 3. So we get here g3 of t is equal to s3 of t minus s3151 of t s3252 of t. The final output period is 1 when 2t by 3 is less than t is less than t, and 0 elsewhere. As the third basis function of phi 3 is g3 of t by root of 0 to t g3 square of t dt. Hence we get root 3 by t, which varies from 2t by 3 lesser than or equal to t lesser than equal to t, and 0 elsewhere. So here the orthogonalization process is now complete. Let us see the three basis function are phi 1 of t, phi 2 of t, and phi 3 of t from a orthonormal set as shown in the figure. In this example, we thus have m is equal to 4 and n is equal to 3. These are the modes, which means that the four signals are described and do not form a linearly independent set. This is readily confirmed by noting that S4 of t is equal to S1 of t plus S2 of t. Moreover, we note that any of these four signals can be expressed as linear combination of three basis functions, which is enhanced of Gram-Smith orthogonalization process. I thank everyone for watching this video. Please like, share, comment, and subscribe. Thank you so much. I'll meet you in the next video. Bye bye.